Hi, this is Michael Borenstein, and my goal in this video is to provide a demonstration of CRT-Power, a program to compute power analysis for cluster randomized and multi-site trials. Rather than talking about the program in the abstract, let me open the program and walk you through an example of designing a study. Let me start up the program. Let's assume that we're planning a study where the outcome is the SAT score. We're going to be looking at students who are nested within classes, within schools, and within districts. We're comparing scores for treated versus control. When the program opens initially, there are two levels, which are called subjects and level 2s. We're going to go to click on levels, add a level, levels, add a level. So now we have 4 levels. I want to name them, so I'm going to right click over here. I'm going to enter the names, which are districts, schools within districts, classes within schools, and students within classes. I click OK, and those names have been applied over here. By default, the program assumes that we're going to be randomizing at the top level. We can actually randomize at any level, but for the time being, let's leave it over here. We can set the number of units, the number of districts, schools, classes, and so on manually, but for the time being, let's leave that as 2 districts, 2 schools within each district, 2 classes within each school, and 20 students within each class. We can set the ICC. Let's assume that based on prior data, we know that the ICC for districts is going to be about 0.02, the ICC for schools is going to be about 0.05, and the ICC for classes is going to be about 0.12. For purposes of computing power, the only thing that you really need is to enter these ICCs. But the program lets you take this one step further. If you want to, you can enter the mean expected score for the control group, which we're going to say is an SAT score of 500, and the span of scores for students within classes. Again, you'll note that the program has picked up the labels that we put in before, students within classes, and we're going to say that the span is about 360 points. This is, in other words, within a class, for example, where the class mean is 500, we would expect the student scores to span about 360 points, to range from about 320 to 680. This corresponds to a standard deviation of 90. The span is simply 4 standard deviations. And what's nice about this is once you've put in the span for students, the program takes the ICCs that you've entered for the other levels and translates them into spans. All of this is computed automatically. So for example, the ICC for districts of 0.02 tells us that we would expect the district means to span about 57 points. The ICC for schools of 0.05 tells us that we would expect the school means within a district to span about 90 points. The ICC of 0.12 for classes tells us that we would expect the class means within a school to span about 140 points. And finally, as we said before, we would expect the student scores within a class to span about 360 points. This is very helpful because it lets us have a sense of what the ICC corresponds to in actual scores, and we can ensure that the spans that we're looking at are plausible and are consistent with the kinds of information we've seen in the past. So it gives us some added confidence that the ICCs are reasonable, or on the other hand tells us the ICCs might be suspect. Another thing that you can do is, as we just saw, if you start off with the ICCs, the program will compute the spans for you. In some cases you might not know the ICC, but you might have information about the span of these means. In that case, you can right-click over here, and rather than enter the ICC, you can say you want to enter the span. You would actually enter the span of approximately 57 points for the district means, 89 points for the school means within a district, 139 points for class means within a school, and so on, and the program translates that into the ICC. So if you enter the spans, the program computes the ICC. You enter the ICC, the program computes the spans. In either case, you have to check to make sure that the values are plausible. Over here, we can enter a covariate for each level of the design. For example, in this case, where the outcome is the mean score on the SAT, we might look at a district and say that we're going to use as a covariate that district's mean score on the SAT the previous year. Maybe we're expecting an R-square of about 0.30. Similarly, for the school, we might want to use the mean SAT score the previous year. Maybe that's 0.40. For classes, it might be the mean GPA the previous year, let's say 0.20. And for each individual student, perhaps it's going to be the student's GPA the previous year, and maybe that's 0.30. Note that you actually can enter a covariate or more than one covariate for every level of the design. And this is very helpful because often covariates will reduce the error term and substantially increase the power. We have the option in some cases of setting the statistical model. Random means that we have sampled units, we've sampled districts at random from all possible districts. In some cases, there's the option of using the fixed effect model, which means, for example, that if we change this to fixed, this means that whenever we have sampled a district, that we're going to be including all of the schools in that district, so there's no sampling at that level. That's going to increase the power. And finally, we have the option over here of setting the cost for every unit. So let's say that for every district that we enroll, we're going to be spending about $4,000. For every school that we enroll, we're going to be spending about $3,000, or for every class that we enroll, once we've already enrolled the school, that's going to cost us about $500. And for every student that we enroll, once we've enrolled this class, we're going to be spending about $50. Over here, we can enter the effect size. The program allows us to set the effect size to be the standardized mean difference D, which can be standardized either by the standard deviation within clusters or across clusters. Alternatively, we can select the odds ratio as the effect size. At the moment, we're using the standardized mean difference D, and let's set that value to 0.5. Over here, we can modify the value of alpha and whether it's a one-tailed or a two-tailed test. Over here, we can decide that we want to show power using digits. So what we see initially is that given these very low number of units, given this effect size, these ICCs, covariates, models, power is going to be about 12%. Let's assume for the sake of argument that we want to find a design that's going to yield power of 80%. We can do that by trial and error. Not a good idea, but let me just show you how that would work. I can set, maybe we're going to be talking about 3 districts per treatment. Within each district, we're going to have, let's say, 5 schools. Within each school, we're going to have maybe 4 classes. And then we're going to increase the number of students per class, say up to 35, and let's bump this up 1, and we'll bump this up 1, and we'll bump this up 1 more. And so we have found a solution, or we're about to, that will give us power of 80%. It's going to give us power of 80% at a cost of about $600,000. And you actually can manipulate these by trial and error and get a power of 80%. The problem is that when you're dealing with a multi-level trial, there are essentially an infinite number of combinations of units over here that will give you power of 80%. And some of them are going to be relatively inexpensive, and some of them are going to be relatively expensive. It's almost impossible to find the most cost-effective combination of numbers by trial and error. The program has a wizard called the Optimal Design Wizard, where we can simply click on this, click Compute, and the program comes up with a combination of numbers. This would be 6 districts, 2 schools per district, 3 classes per school, and 8 students per class. That's going to give us power of 80% at a cost of about $150,000 as compared to the $600,000 that we were going to spend. So basically this study would cost about 25% as much as the study that we came up with by simply manipulating the numbers. I can paste those numbers in and we see them over here. These numbers are based on the program in computing this set of numbers takes into account the ICC at each level and the relative values of the ICCs, takes into account the covariates, and of course takes into account the cost at each level of the design. The program has the option to find the minimum detectable effect size. So let's say, for the sake of argument, we were to say that we can afford as many as 10 districts, and we want to know what is the smallest effect size we'll be able to find. We click on Find MDES, and the program tells us that with this number of districts, schools, and so on, and these other parameters, we can have 80% power to find any effect size as small as 0.317. Let me bring this back to the way it was a minute ago. Something else the program will do is it will generate a report for you. The report has an executive summary that summarizes everything that we've done. It includes a copy of the table. This is very easy to paste into any report that you might be preparing. Something else that it does is it has a much more detailed report that gives an extensive discussion of every one of the assumptions that we've made in doing the power analysis. And this is really meant to be something you can sit down and study and make sure that every one of the assumptions that you actually have made is the assumption that you intended to make. And if there's any ambiguity, this is a good place to resolve it. Go back and recompute the numbers. You'll see there are many tables in here, both the one that we saw on the main screen and also a series of additional tables that show how many of these numbers were computed, so that there's absolutely no room, or to the extent possible, there's no room for misunderstanding. Something else that you can do is you can create a graph. When you do this initially, the program just generates a graph. By default over here, the x-axis is the number of districts per condition. One of the nice things about the graph is that you can click on any point and the program shows you precise information for that point. For example, over here, the number of districts is 6.2. That's 6 treated and 6 control. The cost would be $184,000. Power would be about 90%. Over here, power is going to be about 95%. 7 districts per condition. The cost is $215,000. It might be helpful to actually see a graph of cost as well. One thing we can do over here, at least temporarily, is to get rid of the footer to give us a little bit more room to play with. We can add over here cost to the graph, and we actually see how for power of 95%, it's going to cost us about $215,000. For power of 90%, it's going to cost $184,000, and so on, so that we can come to an appropriate balance between these. Sometimes you might want to add a second factor to the graph. For example, maybe we want to add the effect size. We've assumed that the effect size is 0.5, but what if the effect size is 0.4 or 0.6? We add those, and now we get a graph that shows all 3 effect sizes as well as cost. Again, you can click on any number over here. So for example, if we decide to power the study for an effect size of 0.5 and we want to get power of about 80%, that's going to cost about $155,000. If the actual effect size is 0.4, then power would be 62%, and if the actual effect size is 0.6, power would be 92%. So basically we're saying we're going to have power of 80% for the medium effect size. If the effect size is higher, power is going to be over 90, but if the effect size is lower, power is probably not going to be quite adequate. Or we can move over here and look at power for the 3 numbers. One more thing that we can do is we can actually move this mark along, and as we do that, of course, these numbers change. We can also create a table that shows the same information that we had on the graph, and these two are linked. So for example, if I click on this number over here, the program then highlights the corresponding number on the graph and shows me the information for it. By contrast, if I come over here and click on this number, the program finds the corresponding number in the table. I can take this table and save it as an Excel worksheet. I can take this graph and save it in a format that can then be imported into PowerPoint or Word. Let's come back to the main table for a minute. There are a couple of other things over here I'd like to show you. One of them is the interactive guide. A nice thing about this is that it basically holds your hand and walks you through every step of the process of computing power. For example, for the effect size, it explains exactly how to select the effect size, how to modify it, and so on. Alpha and tails, there's a section over here called number of units, ICC, and span of means. As you click on that, it highlights the relevant part on the screen. It shows you how each of these is defined. It explains how to modify them, and so on. Also, for each of the chapters, as it were, you actually can click on the word PDF, and it will show you a detailed PDF relating to that particular part of the program. Or you can click on video, and it will open up a video that shows you exactly what that part of the program means and how to use the program to do everything that we're talking about. Over here, it's giving an example of how you would enter the means, the span, and so on. So basically everything that I've been showing you over here in this video, the program will then show you for that specific part of the program. And if you're only using the program a few times a year, this is a very useful way to sort of get back up to speed. There's a second part of the help system, which is something called Show Details. If you click on that, and then you click on any particular item inside the screen, it explains for that item what it means, how it's defined, what the possible range is, what the impact is of setting this, what the impact of setting it would be on power, what the current values are, and how to modify them. And you can do this for essentially anything that you see on the screen, and it gives you that information for that particular column and that particular row. For example, over here we've clicked on this, and it says covariates for an R-square for classes. A study will include one class's level covariate with an R-squared of 0.2. Something else that you can do on the main screen is you can save the scenarios. So for example, over here I can take all of this information, click Add, I can give this a name, and it will save everything that we've done over here. Let's just call this a, we'll edit that, we'll call it a 4-level randomized hierarchical design, and we're going to save that. And let me just put that away for a minute by closing it. Let's assume that we now want to go and explore an alternative design. So far we assumed that we're going to randomize districts, but what if we want to randomize schools instead? It's fairly simple. We just right-click over here and say that we want to randomize schools, and since we're randomizing at this level, everything above that is blocked, everything below that is nested. Similarly, we can if we wanted to, we can randomize classes. This becomes blocked, this is randomized, and this is nested. Or we can randomize students, in which case all of these are blocked, and this is randomized. And you might notice that since we can have a 2-level, 3-level, or 4-level study, and we can randomize at any of the levels that we choose, we actually have 9 possible designs. And since we can do this for continuous data or for binary data, there are a total of 18 designs that are covered by the program. And critically, they all use exactly the same interface so that you can move back and forth between them very easily. In this case, I'm going to assume that we'd like to randomize schools and block districts. We can come back over here and say that every district is going to cost us $4,000. When you're matching at any level, now in order to compute power, you also have to talk about how the effect size varies at that level. So remember before, when we were looking at ICCs, we talked about how the mean score varied from one district to the next. Now that we're talking about blocking districts, we have to talk about how the effect size D varies from one district to the next. And again, over here, the program does allow you to enter the actual variance of the effect size, but generally people are not going to find that to be an intuitive value. A much easier option is to enter the span of the effect size. So the overall effect size is 0.5. We see that over here. The span of the effect size, as we're saying, is 0.5, which means that the D value will vary from as low as 0.25 in some districts to as high as 0.75 in others. And the program then shows us the variance of the effect size. This is now going to be taken into account when we compute power. Again, we have the option of going back and using the optimal design wizard and asking the program to find the most cost-effective design for this. And it turns out in this case, it's also about $153,000 with 6 districts, 2 schools per district, 3 classes per school, and 6 students per class. Again, we can go ahead and generate a report that discusses that. We can copy this into the Word if we wanted to, and we can go ahead and generate a graph and so on. So that's a very quick overview of the some of the more important features in the program. Of course, you can go ahead and save the file, open it up next time. Oh, I'm sorry, I forgot to show you about the scenarios. If we come back over here, I can add this scenario, and maybe we want to compare these 2 versions of the study. I can always click on, this is the one we've just added. If I want to click on this one and restore it, it simply brings that one back. So I can have any number of versions of the study and switch between them very quickly without needing to go back and modify all of those things. When I save the file, I can have 10 or 20 or 30 different versions of the study in here. They are all saved as part of it. A word about our company. We've been producing programs for power analysis since 1985. In fact, we have the world's best-selling program for power analysis called Power and Precision. We also have the world's best-selling program for meta-analysis called Comprehensive Meta-Analysis. Most of our work has been funded by the National Institutes of Health. We have a total of about 50,000 clients. This is a very small sampling of the universities that are currently using our program, some of the medical centers that are using our program, some of the government agencies that are using our program, some of the pharmaceutical companies that are using our program. Our program, in fact, is currently being used in some 67 different countries around the world. The website for this program is CRT-Power.com. We're going to be updating that website fairly soon, but it is active and you can download information over there. Our phone number is over here. I am very happy to acknowledge the funding that we received for this program from the National Institutes of Health. In particular, Dr. Augie Diana at the National Institute on Drug Abuse was the program official for our SBIR grant. The primary developers of the program were myself, Michael Borenstein, and Larry Hedges. We'd also like to acknowledge the help provided by Mark Lipsy, Steve Raudenbush, Jessica Spybrook, and Chris Rhodes. Thank you very much for your attention. If you have any questions, please email me, info@crtpower.com, where CRT Power is spelled over here. Thank you for your attention.